All right, so deviations from Raoult's law now. All right, so looking at azeotropes, things that deviate from Raoult's law, we're gonna have to look at the negative and the positive deviations. I've noted that Cape asked us to look at the graphs for these actually, and I don't know if there was a graph question, but I think I remember doing somewhat a graph question while doing past papers and stuff. So, like, how does the graph look if it positively deviates, stuff like that. So let's try to remember that. All right. So positive deviations, right, from ideal mixtures, right? So positive deviations. The positive deviation occurs when new interactions are weaker than the older ones. Full stop. So if you have a piece of paper and you just write positive deviation from ideal mixture, the first point, the new interactions are weaker than the old ones. Full stop. Right? The vapor pressure of the mixture is higher than predicted by Raoult's law. That's what this means. This is what this meant. The pressure here, pressure solution is higher than when it's ideal. That is what the positive deviation speaks about. So let's go back here. So the vapor pressure of the mixture is higher than that predicted by Raoult's law. Alright? This occurs when the forces of attraction between the molecules in the mixture is weaker than the forces of attraction between the molecules in either of the pure liquids. As a result, the molecules cannot escape the surface of the liquid, right? As readily, right? Let's get an important azeotrope that may be oil and water. I don't know. I think you should look at the molecular interactions between oil and between water and see whether or not that is an azeotropic mixture. See whether or not that is a positive deviation from an ideal mixture. I want you guys to tell me, is oil and water a positive deviation or a negative deviation? You can tell me after we do both, alright? Enthalpy of mixing these liquids is endothermic. Alright? Alright. Extra energy needs to be absorbed. I'm not even going to go through that statement. It's on the slide for you guys though, but everybody should know that from CSEC chemistry, right? And refreshed in unit 1. So looking at the graph for positive deviation, look how it bends up. Ideally, remember that Raoult's law says directly proportional, therefore Raoult's law will give us a straight line. But the positive deviation will give us a pressure curve that is above. Right? So it curves upwards. That makes sense. Hopefully that makes sense. Alright. Okay. The boiling curve will go down. So the positive deviations in Raoult law, for example, two immiscible liquids, ethanol and cyclohexane is an example, right? So the cyclohexane molecules get in the way of the hydrogen bonding of the ethanol molecules, right? So there is net bond breaking, right? So what's happening here, sir? It should be no. It should be no, sir. Please. I think somebody should really fight the person who makes these PowerPoints. There should be no bond breaking at all, right? So there is generally no. There's not bond breaking. So, all right. Okay. So what's happening here now? Right, the vapor pressure itself will actually be above what is predicted by the law, right? So the molecules in the mixture are more likely to escape from the liquid to the vapor, right?
Pardon, sir?
Are you hearing what I'm saying? So what we're saying here is that the for the vapor composition graph, right? The vapor pressure will actually be above or dip above, right? Or it would be dip above. That's contradictory, right? It will basically be above the curve, right? It will bend above the curve itself, right? So the positive deviation, you're gonna have minimum enthalpy, right? That minimum enthalpy is positive, right? And A and B interact weakly with one another.
Sorry, can I break it up?
I'm breaking up. Hmm. Mm-mm. Am I breaking up for anyone else except for Mindy and
Yes, sir. So you're kind of breaking up.
Is it better now? Is everything better now? Hmm. Can you guys hear me better now? Can you guys hear me at all? All right, let me see. I think I got muted. Mm-mm. I'm not. Can you guys hear me? Hello, hello, hello. Is everything a bit better?
Yes, sir.
Okay, so it's good enough for us to continue. Okay, so we're gonna continue. So for our positive deviations, we're gonna have for the vapor pressure composition graph, we're gonna have an increase in the vapor pressure, right? And we're gonna also have here we know that our enthalpy change is gonna be positive, right? And A and B interact weakly with one another in the liquid compared to one another. All right. So we have that there. And for the boiling point composition curve now, it's gonna be dipping under. All right. So we're gonna have the interacting very weakly. It's gonna be the same. It's gonna be the same thing, right? Same thing, but it explains both. And now hopefully you guys can understand, right, how these characteristics influence the change within these curves. All right. Any issues with these curves? Any questions? Any questions? Any concerns? Any emotional outbursts? All right. Seems like everything is fine. So just drop a one in the chat if everything is okay. If you're good with everything here. Waiting for that one. Hmm. Are you guys hearing me currently? Shanique, can you still hear me? Okay, you want us to cover it again. Alright. So what we're saying is that if we're deviating from from ideal mixtures, we're gonna have a non-ideal mixture. And we have two different types of deviations, positive and negative deviations. For positive deviations, then we're looking at the fact that we're looking at the fact that our pressure is gonna be a little bit higher and our boiling point is gonna be a little bit lower. And that's gonna be our positive deviation, right? Why is it a positive deviation, or why do we describe it as a positive deviation? We looked at it here, right? It generally is positive when the pressure is higher than ideal and exothermic, right? So looking at here now, the pressure is going to be higher than the ideal pressure, right? So we're going to have an increase in pressure, and that would mean that the boiling point is going to be lower, right, for this positive deviation, all right? So that's what's going to be happening here. And this is generally because of the weak interactions, right? If you can have a weak interaction in a liquid, the boiling point is going to be lower. We know that. And if the interactions between liquids are very weak, then they're gonna have a more chance to evaporate, right? And you guys should remember that. All right. So that's it there. So that's the vapor composition curve, right, or graph, and the boiling point composition for the positive deviations. While for negative deviations, no, the vapor pressure of the mixture is actually lower than predicted by Raoult's law. So this occurs when the forces of attraction between the molecules are much stronger. So we're just looking at the forces of attraction. That's one thing that we stated in the beginning of this topic, that the molecular interactions or intermolecular interactions between everything, right, is going to play an integral role. So if you mix two things that are not really good at interacting, that are two immiscible liquids, we're gonna have a positive deviation. Vapor pressure is gonna be higher than expected. Boiling point is gonna be lower than expected. But if you're gonna have a negative deviation, what if you're this is gonna happen if you mix two liquids that are strongly attracted to each other? What you're gonna get is a vapor pressure that is lower than expected and a boiling point that is higher than expected, right? So that's what's happening there, right? And your enthalpies will be negative, okay? And in this case, we're using methanol and water, right, that have strong attractions between them, right? So it's stronger than methanol alone or water alone. Because remember, with ideal solutions, they act as if they were alone. So if their interactions are stronger together than alone, then we're going to have a negative deviation, right? Pressure is lower than expected, boiling point higher than expected. All right. Are there any issues here? Hopefully, there are no issues there.
Yeah, can't you listen one more time, please?
All right. So the difference between positive and negative deviations are their interactions, right? So if you're gonna have negative deviation, right, what you're gonna have to do is mix two liquids that have very strong interactions, right? Methanol and water is the example. So the thing you know, methanol interactions are pretty strong. Water interactions are pretty strong. But if you mix methanol and water, that is stronger than pure methanol or pure water. So this mixture has intermolecular interactions that are stronger than their pure counterparts. So that's going to contribute to a much stronger surface tension, right? Much stronger interactions with molecule means that you require more energy, right, to actually boil the liquid. So you're gonna have a boiling point larger than expected. And if you're gonna have such strong interactions, a lot of the molecules are not gonna want to evaporate because they're strongly bound in the mixture. Therefore, the vapor pressure will be lower than expected. All right. That's the same for positive deviations, where in positive deviations, the molecular interactions are so weak that you don't require much energy to really boil the substance, so it's going to dip under the expected, right? And since it's gonna have such weak interactions, it's gonna be really easy for them to evaporate, so the vapor pressure is gonna be higher than expected. Hopefully that makes sense. Hopefully that put everything together. All right, for that. Now, really and truly, we have some questions to answer. All right, I want you guys to have a go at these questions. I know that you guys have all of the other subjects to study, and you guys have schools and stuff like that, right? And this is just an extra session. But see if you can define these things. If you can answer every one of these questions, you should be more or less good. You should be able to define what a Mohs fraction is. State Raoult's law in its general form with respect to solutions. State Raoult's law for a solution containing volatile components. Explain how the vapor pressure of a solvent is affected when a non-volatile solute is dissolved in it. Define an ideal solution and write one of its characteristics. Write two differences between ideal solutions and non-ideal solutions. Right? And the last thing, on mixing liquid X and liquid Y, the volume of the resulting solution increases. State the type of deviation from Raoult's law shown by the resulting solution, and state the change in temperature that one would observe after mixing liquids X and Y. Now that number 7 is a very interesting number 7. But if you guys are able to get through these questions, answer it, and know why the answers are correct or incorrect, this should be more or less fine, and you should be ready for your solvent extractions. All right. I will. Okay. You see, I like to. Okay, hold on. Let me end the recording first.